This is another example of problems or algorithms fall under greedy design strategy or greedy design technique called the Dijkstra Algorithm, for the single source sorted file problem, defined as given a weighted connected graph, weighted with the weight and connected with connect the vertices with the edges. Find shortest path from source vertex x to each of the other vertices. So Dijkstra actually similar to the minimum spanning tree algorithm with a different way of computing numerical level among vertices not already in the tree. It finds vertex u with the smallest sum here with this formula, the distance here. Weight is a b and u, where b is a vertex 2 for which shortest path has been already found on preceding iteration, such vertices from a tree, which is b here, and dv is the distance. So where the distance is the length of the shortest path from source to b, wvu is the length width of h from b to u. Okay, look at this graph. Let's say we have A, B, C, D, E with the weight here A to B 10, A to C 3, and after that C to B 4, B to C 1, C to E 2, and B to D 2, and C to D 8, and D to E 7, and E to D 9. Now, this is actually the vertices here A, B, C. So the first as pre-processing A to A basically 0, the distance. A, B, C will initialize as the infinity here because the first we don't have the we don't know that the weight, and we have the set here. And finally, based on this, you can see that from the A to B, basically 10 here, 10, A to C, 3. With this infinity, A to B, A to 10, A to B, A to C. And now these are the set of A, which is A to B, A to C, the source here. And from there, the minimum is a 3 compared to 10 here. So let's say we have to choose the A to C here with a 3. And finally, the net is A to B. From here, this is a minimum. In order to go to B, so we have to add that this 4. A to B, this is a minimum, and this also the minimum. There's no way to go to B instead of through C to B here, because 10 to B is actually equal to, A to B here equal to 10. This is actually the greater than A to C, and here, and 3 plus 4, so this 7, and to D here, to D maybe we can go to A to C, 3 plus 8, 11 here, through E actually 5 here. So in order to go to E, so we can go to A to C, C to E, because it is the minimum. Okay. Net is, for the E is actually, instead of we go to A to C, C to D, D to 7, so the minimum is A to C, C to E. So that's why we got this A, C, E. Okay, this is actually the minimum sorted path. And finally, we update again, still A, C, E. And finally, for the 7, this is actually the minimum A to B. In order to go to B, so you have to go to A to C, C to B. Here, not A direct to B. Okay. And after that, 6 here, A to C, 3, 3 to B, 7, and B to C, 2. So A to C to B to D here, A to A to B, sorry, A to C, the minimum, and after that C to B, which is 7, and B to D. This is actually the minimum. And finally, for the D is 9 here. In order to go to D, D is A to C, A to C, C to B, B to D. Okay. So note on Dijkstra algorithm doesn't work for graph with negative weight, only for the positive weight. Applicable for both undirected and directed graph. As you see, is OB squared. B squared is a vertex squared. Is similarly we can show that n squared for graph represented by weight metric and array by using the matrix representation here. But for the adjacent link list here, it will end up of big O of E times log B. E for the edges, B for the vertex. So E times log B here. Maybe we can assume that's similar to n log n. Don't mix up this algorithm with frame algorithm because it is a difference with the this for the subtle